Okay, in this video we are going to discuss center of a tree. So we will go through some basic definition and we will prove a statement related to the center of a tree. Okay, so let me start by reminding you of some basic definitions related to the center of a graph. So already we discussed the definition in a previous video. So for more details you can look into that video. Okay, so let me remind you of the eccentricity of a vertex, the radius of a graph, and the center of a graph. So let V be a vertex in the graph G, then the eccentricity denoted by E of V is defined as follows. The eccentricity of a vertex V is the maximum among all the distance between that vertex V and all other vertices in the graph. Okay, so it is going to be the maximum of all the distance of this vertex V and all other vertices in the graph. Okay, so let's look into one example. So consider this graph G and let's find the eccentricity of each and every vertex in this graph. So eccentricity of V1 is nothing but the maximum among all the distance between V1 and all other vertices in the graph. So here the distance between V1 and V2 is 1, V1 and V3 is 2, V1 and V4 is 1, 2, 3. Okay, so we have 1, 2, 3 here, and V1 and V5 is again 1, 2, 3, and V1 and V6 is 1, 2, 3, 4. So we take the maximum among all those distances. The maximum is nothing but 4. So that says the eccentricity of V1 is 4. Similarly, the eccentricity of V2 is 1, 2, 3. Eccentricity of V3 is 1, 2. Eccentricity of V4 is 1, 2, 3. And also we could consider this path 1, 2, 3. Okay. And eccentricity of V5 is 1, 2, 3. And eccentricity of V6 is 1, 2, 3, 4. Okay, so these are the eccentricities of the vertices in this graph G. Okay, so once you have defined eccentricity, we can define what is called the radius of a graph. So remember, the eccentricity is defined with respect to a particular vertex and the radius is defined with respect to the entire graph. So the radius of the graph is nothing but it is the minimum among all the eccentricities of the vertices in the graph. So let's go and find the radius of this graph. So the radius of this graph is nothing but the minimum among all the eccentricities here. Okay, or eccentricities of all the vertices in the graph. So here the eccentricities of all the vertices are 4, 3, 2, 3, 4, and minimum among all these is 2. So the radius of this graph is 4. Radius of this graph is 2. Okay. And once you have the definition of radius, we can define what is called a central point. So a vertex V is called a central point if the eccentricity of that vertex is equal to the radius of the graph G. Okay, for example, if you look into this graph, we can see that okay, here if you look into the eccentricity of V3, E of V3 is exactly equal to the radius of the graph, which is equal to 2. Okay, that says V3 is a central point. Okay, so V3 is a central point. V3 is a central point of this graph G. Okay, so a graph in general could have more than one central point. Okay, in this case it happened to be a graph with only one central point. Okay, once you have the idea of this central point, we can define what is called the center of G. The center of G is nothing but center of all central points. Okay, set of all central points is what is called the center of G. Okay, for example, if you consider this graph, the center of this graph G is the set of all central points. This graph it have only a single central point. Okay, so here this set contains V3. Okay, so these are some basic definitions we need to talk about the center of a tree, the eccentricity, the radius, and the center of a graph G. Okay, so once we understood all these definitions, let's go and look into the statement related to the center of a tree. So every tree has a center consisting of either one vertex or two vertices, and if the tree has two centers, then those vertices must be adjacent. Okay, so the statement reads as follows: every tree has a center consisting of either one vertex or two adjacent vertices. So a tree cannot have more than two centers. It could have one or two. Okay, if it have two, then okay, those centers must be adjacent also. Okay, so let's look into one or two examples before proving the statement. So let's look into this particular tree, say T1. Okay, so here I labeled the vertices by the eccentricities of those vertices. The eccentricity of this vertex is 1, 2, 3. Okay, and this is 1, 2, 3. Okay, and the eccentricity of this is 1, 2. Okay, so I labeled this one, and here we can see that if you look into this graph, the central points, central points in this tree is this vertex and this vertex. Okay, here we can see that the radius of this graph is 2, and these two vertices have the radius exactly equal to the eccentricity of that vertex. So these two vertices are the central vertices. Okay, and these two vertices are also the center. Okay, center of this T1. Okay, so this graph, it has two centers. Okay, and according to the statement, this says every tree has two. That's true for this also, and if that's the case, if it has more than one, then the two vertices must also be adjacent. Okay, we saw it from here. Okay, so let's look into this example, and again I labeled the vertices by the eccentricity of that particular vertex. Okay, that says the eccentricity of this vertex is 6. Okay, the path corresponding to that number will be like 1, 2, 3, 4, 5, 6. Okay, and similarly the eccentricity of this is 6, and so forth. Okay, so if you look into this graph, we can see that so this is the central point. Okay, and here if you look into this tree T2, you can see that the center of this graph T2 is 3. Okay, and it has only as one central vertex. So here this 3 is the center. Okay, it is the center of this graph T2. So this graph, it happened to have two centers, and statement says if a tree has two centers, then they must be adjacent. Okay, that's true for this one, and here this graph, it has only one. Okay, and the statement says every tree has a center consisting of either one vertex or two adjacent vertices. Okay, so let's go and prove this statement. Okay, the proof idea is as follows. So here if you look into this particular graph, we can see that this is the central vertex. Okay, this is the center of this graph. So proof idea is as follows. So what we do is, okay, here we can observe some important thing. Right here we have these 4 leaf vertices. Okay, and suppose that we delete these 4 vertices. Okay, if we delete all these vertices, all these leaf vertices, for example, okay, we get this graph. Okay, or this tree. So if we look into that particular tree, we can see that okay, the eccentricity of all the vertices will get reduced by 1. Okay, in the remaining tree. So the new eccentricity here will be 1, 2, and the new eccentricity will be 1 here, and the new eccentricity will be 2 here. Okay, so that says if you delete all the leaf vertices, and if you look into the new tree, okay, we can see that the eccentricity will uniformly get reduced to 1. So that says the center, it won't change. Okay, and again what we do is we will consider that reduced tree and we delete the leaf node. Okay, so we delete this node here and this node. So we are left with one vertex here, and that one vertex will correspond to the center. Okay, so let's look into one more example. Okay, a tree that has two centers. Okay, we already discussed this particular tree. So this has two centers, right? So if you label the eccentricity vertices with the eccentricity, here we get 1 2 3 here, 3 here, 3 3, and the eccentricity of this vertex is 2 and the eccentricity of this vertex is 2. Okay, so here again if we delete all the leaf vertices, okay, these 4 vertices, we are left with this one. Okay, so what we do is we delete these leaves until we have a k1 or k2, a complete graph on one vertex here. Okay, somewhat similar to this situation, and here we have this k2 and we stop there. Okay, and here we can see that okay, after deletion anyway the eccentricity will get reduced by 1 uniformly. But the thing is that okay, here okay, after deleting all these vertices we have this k2, right? Okay, and that corresponds to, and those two vertices corresponds to the center. So here okay, these two vertices corresponds to the center of this tree. Okay, and again we can see that a tree could have either one vertex or two adjacent vertices. Okay, here 1 and here 2. Okay, so let's go and prove. Okay, here we can see that for okay, sorry, for k1, a complete graph on vertices or one vertex, we have a situation something like this. So here this is going to be the center, so the result is true. Okay, and similarly for k equal to 2, okay, we have okay, this tree, and here we can see that okay, these two vertices, okay, these two vertices are the center of this tree. Okay, and again we can see that the result is two adjacent vertices, and these vertices corresponds to the center of k2. Okay, okay, so let's go and prove for k greater than or equal to 2. Okay, so let T be a tree with say greater than or equal to 2 or greater than 2 vertices. Okay, so since we are dealing with a tree, and if a tree has greater than 2 vertices or greater than or equal to 2 vertices, we can see that okay, we already proved this statement. It has at least 2 pendant vertices. Okay, so let me write down what I said. Okay, since T is a tree and the number of vertices is greater than or equal to 2, then T has at least two pendant vertices. Okay, and here another observation is that the maximum distance from a given vertex to any other vertex occurs when the other second vertex is a leaf vertex or a pendant vertex. Okay, so that's what we can observe from this thing, right? So here if you look into this particular vertex, so maximum distance occur when the other vertex is a leaf vertex. Okay, so in order to find the maximum distance between this vertex, okay, that corresponds to eccentricity. What we do is okay, we will consider the distance between this and all the leaf vertices and take the maximum. Okay, so we take the distance between this and this, okay, this and this vertex, okay, only need to consider the leaf vertex. Okay, that will correspond to the maximum distance. Okay, so the maximum distance from a vertex, say u, to any other vertex okay, it occurs when any other vertex, say v, occurs when v is a pendant vertex. Okay, so since we are dealing with a tree, okay, a tree has at least two pendant vertices, and again we can see that the maximum distance from a given vertex u to any other vertex v occurs when this v, the second vertex, is a leaf vertex or a pendant vertex. Okay, so next what we are going to do is, as we did here, we are going to delete all the pendant vertex. Okay, so delete all the pendant vertex from delete all the pendant vertices from T. Okay, and let the resulting graph is a T dash. Okay, so the resulting graph so let's call that graph T dash. Okay, it is also a tree. So we took a tree and we deleted all the pendant vertex. Okay, so we still have a tree, and the resulting graph T dash is also a tree, and we can also see that the eccentricity of all the vertices in T dash is uniformly reduced by 1. Okay, and that says the center of T dash, okay, will be equal to the center of T. The centers won't change in this process. So the resulting graph T dash is also a tree, and also we can see that the eccentricity of each vertex in T dash is exactly 1 less than the eccentricities of those vertices in T. Okay, so the eccentricity of each vertex in T dash is exactly one less than the eccentricities okay, each vertex is less than, okay, exactly 1 less than the eccentricity of that vertex in T. Okay, and because of the reason we can see that therefore T and this T dash have the same center. Okay, so again what we do is we will consider this t dash, and t dash is also a tree. Okay, and if it is not k1 or k2, okay, again it has at least two pendant vertices, so we remove those pendant vertices and we get a new tree. Okay, and we can use the same kind of argument, and we can see that okay, that t double dash will also have the same center. Okay, and we will repeat this process until we have a single k1 or k2. So if we are left with k1, then that corresponds to the center of the tree, and if you are left with k2, okay, then those two vertices correspond to the center, and again we can see that those two vertices are adjacent. Okay, so from t dash we again remove all pendant vertices and get another tree, say t double dash. Okay, and again we can see that t double dash is also a tree, and all the vertices in t double dash have eccentricities 2 less than the eccentricities of the vertices in t, and maybe 1 less, and also 1 less than the eccentricities of those vertices in t double, okay, t dash. Okay, but again we can see that the center remains the same, so that says the center of t dash, t double dash will be equal to the center of t dash. Okay, and that will be equal to the center of t, and we repeat this process until we are left with either k1 or k2. Okay, so from t dash we remove all the pendant vertices and get another tree t double dash. Okay, so we continue this process. Until we are left with a vertex. Okay, in that case, okay, that vertex will be the center. So which is the center of T or an edge. Okay, in that case the endpoints of this edge will act as the center. Okay, and again we can see that they are connected by an edge, so they are adjacent. So whose end vertices are the two centers of T. Okay, and that's the proof. So hence the theorem. Okay, so this proof not only proves the theorem, it also gives a method to find the center or the centers of a tree. Okay, so that's it. So okay, we saw from anywhere these two examples. Okay, so here again if you run that particular proof on this tree, okay, so we can see that in the first step, okay, we will delete the center. Here is this tree T, right? So let me use a different color. Okay, so in the first step what we do is we will delete all the pendant vertices. Okay, so we will delete all these, okay, and these two. So we can see that after deleting all these, the eccentricity will get reduced by 1 on the remaining tree, right? So the new eccentricity will be 4 here, 3, okay, and here 4, 2, 3, 4, and again we can see that the center, it won't change. Okay, so in the next step what we do is we will consider this new graph. Okay, and we will delete all the pendant vertices from that graph. So we will delete this one. Okay, so in the first step anyway we deleted this one, right? Okay, so I think in the first step we deleted this, right? Okay, and we delete this 5. So we are left with this path here. Okay, and from that we delete okay, we can see that the eccentricity will get reduced by 1 again. So the new eccentricities will be like, for this vertex it will be 2, and for this vertex it will be 1, and for this vertex it will be 2. And again we can see that the center of the that T2 double dash is still this vertex, right? Okay, so from you can see that the resulting tree is not K1 or K2. So we will delete okay, these two vertices. Okay, these two vertices from the T2 double dash, we get T2 triple dash, and we are left with a single vertex. Okay, and that single vertex corresponds to the center. Okay, so okay, so that's the proof. Yeah.